timing.
Nice.
And it's a great pleasure to introduce Olson from Renewable, and he will continue sort of the trend we heard yesterday and today and talk about interfacial control in OPV devices.
Thank you, Natalie. First, I'd certainly like to take the opportunity to thank the organizers for inviting me to speak here. It's fun to be in a little bit different community, a little different environment, and hopefully a little less formal. Should I speak louder or do you need a microphone? Is that better? There you go. Thank you, yeah. Okay, so I'm going to talk a little bit about, honestly, the application and device side of what Aaron's been talking about now for the past couple of presentations, and probably lead into a little bit of what she spoke about yesterday and touch a little bit on what likely Joe Barry spoke about, I believe, last week. I'm going to talk a little bit about interfacial control in OPV devices. We have a lot more stuff going on in the group, but effectively I'm going to try to limit this to basically build off of what Aaron has already presented. So this is obviously not a one-person show. This is a group of rather large proportions in the sense that we have quite a few postdocs, staff, former staff now. From NREL, we have graduate students and a couple interactions with Ruben Collins, Todd Furtak at Colorado School of Mines. A couple of graduate students here and there. Right now, Edwin Janarka is involved from CU here. University of Denver, including AJ, Brian Bailey, and Sean Shaheen. And Erin Ratcliffe, I think, rises to the top as one of our prime collaborators as well. So you'll see her name on a lot of slides here going forward. Then again, we have interactions with Princeton, as Aaron touched on as well, Georgia Tech for some small molecule modifiers that we're looking at, as well as another interaction with UC Santa Barbara, which I'll touch on for some new absorbent materials that we're studying the contacts of, and then some lifetime stuff that we're doing with Mike McGee, who I think speaks next week. So what I want to really kind of hone in on is what Aaron has already touched on. But effectively, you've already heard it, in order to improve the device performance of these organic solar cells, much has to be done to improve the energy level alignment, the optical absorption, and minimizing the energy losses in the active layer system. And the fact of the matter is, a lot of that's going to be accomplished by just rather simply, but it's much more complicated than that in terms of the actual chemistry, but just moving the energy levels deeper, for example, to reduce the offset between the two limos of the donor acceptor materials. But the fact of the matter is, what happened there is the HOMO level pushes quite deep as well. And so if you use your standard contact, say P.PSS, as I'll go through in the talk, maybe that's not optimized for these new materials. And in fact, yes, what we can do is move the contacts to accommodate those changes in the active layer so as to hopefully optimize the device performance of those systems. One even more important thing that I'll touch on as well is that these contact layers that Aaron and Joe have described already help to basically normalize the device performance from the actual electric or electronic properties of the electrode materials themselves, in the sense that when we use these contacts, we can actually invert the orientation of these devices so that we can actually have electrons coming out into the TCO as opposed to electrons, and or we can change out the the electrodes themselves, move from ITO to something hopefully cheaper and more scalable in that sense. On the back side, in terms of the metal contact, this also allows us to move away from reactive metals such as calcium, aluminum, lithium fluoride, all of these sorts of systems, which also incidentally are not easily solution processed or coded for roll-to-roll applications. Equivalently, we can move the electron affinity of these acceptors, and we should be able to, and we're working on actually trying to modify the electron contacts in these devices as well to accommodate those changes. So I'm going to talk about primarily two OPV device architectures. The first one on the top being our standard architecture, which is basically derived from OLED technology originally. But it's the go-to device architecture for most OPV devices, and this is basically just typically a P.PSS or another whole transport layer on top of ITO, your active layer or your bulk heterojunction. Calcium and aluminum, for example, as a very good electron contact in this system. One of the problems here is that these must be fabricated in inert atmosphere, and that is largely due to the fact that those metals on top are very reactive. And even if you deposit the active layer in air, there's enough water and moisture, oxygen and moisture in that active layers that it'll actually react with the contacts and cause some pretty substantial decreases in performance immediately. Also, these employ these low work function contacts which are susceptible to oxidation. These inverted devices basically use an electron contact on the bottom here. I'm showing zinc oxide, active layer, and then we can put the whole contact on top here, in this case P.PSS, but of course you can use moly oxide or other systems as well. And then we have a higher work function metal contact on top, silver, gold, copper, all of these things that have been used. One advantage to these, especially in terms of scaling up for industry, is these can be fabricated in air, and they use these higher work function contacts that are more stable also for printing applications. So I want to talk a little bit about metal oxides as whole transport layers in standard OPV devices. And to start that off, I just want to show basically what the effect of a whole transport layer is on the device performance. In the black, you have a P3HT PCBM device, which you guys have probably heard enough about, and I won't go into in any detail. This is on top of P-dot as the whole contact with ITO underneath. If we remove that P-dot, you see that you have some rather substantial contact issues to that active layer, in the sense that the fill factor drops dramatically. And depending on the material system and where you process these things can change, but essentially the device performance is always lower without a whole contact intermediate between, say, the ITO and the active layer. What you also see, however, is that without that P-dot layer, you see the series resistance, so the slope here is actually higher, so the series resistance is therefore lower, which that is a good thing, and maybe that's something we can go and try to improve upon in terms of what the P-dot is capable of here. And also you see that without the P.PSS, you're actually extracting more carriers or more photocurrent from the device, and I'll get into a little bit of what's going on in there as well. Other reasons that P-dot is problematic is it's an acidic suspension. It can be neutralized, but still it still has some fairly acidic chemistry that's incumbent in the system. And so that prevents it from being used with zinc oxide, for example, based TCOs, which Joe and Aaron have probably talked about quite extensively. Basically, these things, as soon as you put down this P-dot layer on top of a zinc oxide-based TCO, you end up with a zinc-doped P-dot layer. I mean, the zinc oxide is completely removed. The other thing, too, is that this P.PSS, even after deposition removal of the water, it's still very acidic, and it can actually etch the ITO underneath. And that's obviously a problem in terms of device stability. And in fact, it's very susceptible to water absorption. It's very hygroscopic. And so as it absorbs water, the conductivity of that PDOT layer can change, and the device performance suffers accordingly. This is some data from now 6 years ago out of Imperial College, but I think that shows it quite conclusively that without PDOT, you see fairly stable device performance. With it, device performance drops very, very quickly, and you can see here the scale. This is 0 to 10 hours, so that's quite remarkable changes just in that system there. So there have been a number of reports of metal oxides to be used as hole contacts in organic solar cells. PDOT has been replaced by N-type materials such as moly oxide, vanadium oxide, and tungsten oxide. There are a few others that are kind of being explored, but these are, I would say, primarily the main ones in the literature. Often these are deposited by thermal evaporation. There are a number of reports now, including one from our group where we've done solution moly oxide. A few other groups have done that recently as well. There's a solution vanadium oxide precursor and some nanoparticle tungsten oxide systems that have worked pretty well. Aaron touched on whether or not these N-type materials are actually electron blocking, and I won't go too much into that, but we are actually trying to evaluate that in more detail in solar cells, but effectively they work pretty darn well. In most cases, they're indistinguishable from some P-type contacts. The P-type contacts that we've been working on are nickel oxide. This nickel oxide, as Aaron showed, is P-type. It's wide band gap. You can obviously get quite good performance out of this, as is indicated from this PNAS report a number of years ago now from Tobin Mark's group at Northwestern. So what we have done, and I think Joe would have talked about this already, so I won't go into any details. We've done basically what was reported, although what we see is something that's arguably a different material. But we're doing pulse laser deposition of nickel oxide down on top of the ITO. We put the active layer down on top, and we can get very good device performance. This is with P3HT PCBM. And the black line, which is probably quite hard to see, is PDOT PSS, and the green circles are PLD, positive nickel oxide. You can see equivalent device performance with those two systems. What's interesting is if you don't optimize the deposition conditions, you can actually end up with very, very poor device performance. That's just by basically changing the energetics at the interface, as Aaron talked about in some detail. We're actually still, I think, trying to understand what's going on here, and that's some of the research that Edwin Winjanarkos is undertaking as we speak. But essentially what you see here is the acid-positive films can have very, very poor device performance. The contacts here are so bad that you're getting fill factors less than 25%, which is basically worse than a resistor, right? I mean, that's it's actually quite impressive that they can be so bad. What's interesting is we can actually tune that just by a surface plasma treatment. So if we do an argon plasma, you can see that you have some intermediate performance, still very, very poor charge extraction from that system. But when we do an oxygen plasma, you see it works very well. And if you change the underlying or the deposition conditions of that nickel oxide, during the deposition, you can see you can change the initial performance of the acid positive, but actually the plasma treated systems look almost identical. And we can, of course, put this down on gallium dope zinc oxide and get equivalent performance to ITO-based devices, which is good for moving forward with, hopefully, cheaper TCOs. But PLD is not what I would call scalable. Some might argue otherwise, but in terms of roll-to-roll massive production, it's probably not the way to go. Edwin has done a bunch of work on processing these nickel oxides from sputtering, RF sputtering of nickel oxide from nickel oxide target, and basically same thing here, equivalent device performance to PDOT PSS, in some cases a bit better, depends on the conditions. But one thing we've been working on now for a couple of years is a solution deposited nickel oxide species. And basically this comes from a nickel metal precursor ink that was developed at NREL in our group to actually inkjet print nickel metal grid lines for silicon solar cells. What we did was take that ink, reformulate it, basically dilute it, and then anneal it under different conditions so it would make zinc oxide. We spin coat this just in air. The film thickness is typically 5 to 10 nanometers. And these are, we say, largely amorphous, but we've never observed any diffraction peaks from XRD, even under the synchrotron at SLAC. Some of the properties of this nickel oxide: it is a wide bandgap system, so unlike P.PSS, as you get away from the band edge, the transmission actually improves dramatically. It is very low conductivity as well. And so you can see here, beyond, say, 450, 500 nanometers, you have enhanced transmission through those layers compared to P.PSS. And that's certainly an avenue for enhancing the performance beyond P.PSS in these systems. Aaron's already talked about this. I won't go through it in any detail at all, but basically the work function is quite high, and it shifts based on that oxygen plasma treatment. We do that same treatment on this solution deposited system, and you see the work function increase dramatically. And you see in P3HT PCBM devices, you see enhanced diode quality and VOC in those systems, partly due to the enhancement of the work function in these systems. And there may be some underlying effects that are going on that are leading to particularly bad contact performance in the as-deposited system. Aaron's already talked about all this, but basically you see enhanced hole injection and extraction rates with this nickel oxide, which is much, much better than what you see for P.PSS, which is encouraging for enhanced device performance as well. What you see with P3HT PCBM is, in fact, equivalent device performance. Just like we saw with the PLD and the sputter nickel oxide, again with the solution deposited system. Equivalent VOC, JSC is a bit lower in this case, but this is basically just noise in the devices. They all end up more or less exactly the same. So then the question becomes, what happens with this P-type nickel oxide as we move to deeper HOMO donor materials or higher ionization potential systems? Is there a benefit in this higher work function system when we do that? And so the system that we've worked on is this PCD-TBT. It's a polycarbazole unit here with a thiophene bridge to a benzodiazole or BT unit here. Basically, this is polymerized combined with C70 PCBM. And it's been reported that these systems are measured at above 6%. And that's partially due to enhanced VOC compared to the P3HT PCBM system, where you'll get typical VOCs for P3HT PCBM are on the order of 0.6 volts. Here we're seeing this is closer to 0.9, high 0.8. So this system was actually achieved on PDOT, or that 6% was achieved on PDOT with the TIOX contact in the back. And what we'd like to then do is take and move beyond this P3HT PCBM system, where the work function seems to be very close to the transport level or the HOMO level of the P3HT, as Aaron has described via UPS measurements. And as we move to this PCD-TBT system, we increase the offset between the donor HOMO and the acceptor LUMO, thus increasing the potential energy between those two separated charges. But what you see is at the same time we've increased the distance, the energetic difference between the P.PSS and the HOMO level of the PCD-TBT. So what we're hoping to do is improve that with nickel oxide, and we're not using a TIOX contact in the back because it just doesn't work in Colorado. I think you need that marine layer in Santa Barbara with the loud door open to the beach, and then the stuff works like a charm. But here we have to get by with calcium aluminum. So we're then going to compare it to P.PSS relative to the nickel oxide in that system. And what you see is that the device characteristics improve in all areas. So more or less the VOC is about 0.88 again. Our control with P.PSS is about 845 millivolts. The current does go up a bit. The fill factor increases quite substantially, almost 10%. And as a result, the efficiency out of this nickel oxide-based system is a full percent higher than what we get in our labs with P.PSS. And part of that is because the saturation current, or the dark leakage current in these devices is quite a bit lower. And we'll talk about that a little bit in the future. But basically you can see that in the dark IVs, the P.PSS has a higher leakage current in those devices than the nickel oxide. And that in part is what increases the VOC. The JSC is likely increased because we have an improvement in the absorption or the EQE in the system. With the nickel oxide beyond 500 nanometers, this is undoubtedly related to improved transmission through the nickel oxide. And what's also interesting and good to note is that when we compare the nickel oxide in black to the P-dot in blue, we see enhanced stability or device lifetime, even with, say, a calcium aluminum back contact. So these devices are not encapsulated. We're measuring them under constant illumination and load in light. And you can see over the course of, this is 400 hours, the P-dot decays substantially faster. So to switch gears a little bit and talk a little bit about the role of word function as opposed to band alignment in these contacts with the active layer, I want to talk a little bit about some work that we've done on modified nickel oxide modified ITO surfaces. So what we're doing is we're taking just ITO, which has a word function on our Kelvin probe system of about 4.7 eV. What we can do is take and soak that ITO in these various benzyl phosphonic acids. So more or less what you can see here is you have fluorinated benzyl phosphonic acids, and what we're trying to induce here is an interfacial dipole by putting these small molecules on top of the ITO surface. So we soak these overnight, they form a self-assembled monolayer or SAM layer, and as a result, depending on the molecule we use, we change the word function dramatically. These again are measured via Kelvin probe. We're getting something around 4.4 eV for this ortho-difluorobenzyl phosphonic acid. And when we go to this para-trifluoromethyl system, we see we can increase the word function of ITO only up to about 5.3. And in fact, when these have been measured in UPS, the range here is actually even larger. So there's no doubt some interaction with these surfaces with moisture and what have you in the air where we're measuring these under Kelvin probe. What's interesting actually is that we don't have the same dynamic range in tuning the word function with P-dot or nickel oxide, but it turns out that these, the P-dot pairs up very nicely with this benzyl phosphonic acid and the nickel oxide with this PCF3 system. So basically they have the same measured word function in the Kelvin probe and almost identical in UPS as well. So what this allows us to do then is look at band alignment in these systems, and Erin has talked about this in detail. Basically, she's taken and measured the energy levels of the active layer themselves in terms of the PCD-TBT PCBM system. You see this is the HOMO level of the PCD-TBT, and this is the LUMO level of the C70 PCBM. What we're doing here is depositing thin layers of these on top of the modified ITO, on top of P.PSS on ITO, and on top of nickel oxide on ITO. And what's interesting here to note, and this gets back somewhat to this comments earlier about moly oxide, but I will argue that this is not the same mechanism as what you see there. But what you see here is that, okay, ITO is degenerately doped, transparent conductive oxide, right? Which means that the Fermi level is in the conduction band. So when we measure the band positions using UPS and IPES, you can't actually see the conduction band. All you see is the Fermi level or the word function. So this is the para-trifluoromethyl BPA modified ITO. So this is the highest work function system that we have in terms of the SAM modified ITO systems. And here via UPS, Aaron has measured 5.5 EV for the work function in the firm level on that system. What you note is that while the work function is deep enough, to pin to the HOMO level of the PCD-TBT, there is no barrier for recombination or injection of what I'll call the minority carrier, which is the electron at this interface. By that, I mean, if you have this in reverse bias, you can inject electrons relatively freely into that system, relatively speaking, in terms of when you go to P.PSS, you do introduce a barrier there because it does have a defined conduction band level. When you go to nickel oxide, you see that that barrier is increased from nothing to 0.6 EV to 2.2 EV. So this obviously helps explain then why we might see changes in device performance relative to these systems. If we go in and look at this PCD-TBT, this is a C60 system. You see that the change in work function here, just an ITO again, results in a substantial change in VOC, fill factor, and device performance. So again, there's no HDL here at all. All we're doing is putting a SAM layer down on top of ITO just to locally modify the work function through this interfacial dipole. And what you can see is you have very good diodes throughout. In fact, all of the series resistances are quite low, and actually in the dark they all look very similar until you get into this range into the injection region, where your diode is turning on. Basically, you see the built-in potential, or the turn-on voltage of these diodes is increasing with increasing work function. So, long story short, this more or less helps improve extraction of these devices. It may help to modulate the field in the devices, especially at that interface as well, although we're not sure that you have an actual charge transfer at the interface, which you undoubtedly see with moly oxide, for example. What's interesting is when we go on to compare, say, the same work function for the SAM modified ITO to P.PSS, you see an improvement in VOC again, and in fill factor as well. And when we go to the higher work function systems of this para-trifluoromethyl 5.2 EV or a nickel oxide, we again see an improvement in the VOC in those systems. And as I mentioned earlier, this basically all comes back to decreased saturation current or leakage current in those devices. And this, we're arguing, is related to that recombination barrier, or that barrier for electron recombination at the hole contact, which improves the diode quality and improves the device performance dramatically. So you can see here, even with the same work function, you're still getting almost a full % increase in device performance. So that's to say, even if you have your work function correct, there might still be room for improvement through the development of what we refer to as thermodynamically selective contact. Now, talking a little bit about charge transfer at these interfaces and interfacial chemistry. Aaron mentioned earlier that you can have a favorable charge transfer interactions at those interfaces. And then she talked a little bit about some of the work that she's done on this system, looking at actually detrimental charge transfer. So just to jump into this, we're looking at this small molecule from Greg Welch and Guy Bazan from the University of California, Santa Barbara. This system has recently come out last fall. They had a paper basically showing about 6.7% with this system on moly oxide. But when we started working with this molecule, they sent it to us because they were having pretty substantial problems with it. Or at least they didn't know if they had problems, but they knew the devices didn't work very well. So they would make devices on P.PSS, as everybody does, and they were getting between 1% and 2% on the systems. And lo and behold, we re-optimized these on PDOT in our labs, and yeah, it's about 2%. Initially, they were about 0.8, and you keep optimizing the process, you get up to about 2. What you can see in the blue curve is this very poor fill factor. Actually, it's quite reminiscent of the ITO-only device I showed you earlier with P3HT. More or less, this is some indication that there's collection issues in that device, either from the active layer or at the contacts, and you don't really know which. So what they had suggested, or what we had tried, is basically to increase the work function by using, instead of this P.PSS system, a PlexCore HTL, which is basically an analog of P.PSS, but it doesn't have PSS in it. It's basically a sulfonate bonded to the molecule directly, but effectively it still has sulfonate groups in it. And you see that the VOC improves when you go from a work function of 4.9 to 5.2. VOC improves dramatically, as I showed previously. That's not unexpected because the HOMO level of the system is relatively deep. What you see, though, is the current drops. Actually, the fill factor is even worse than it was with P.PSS. So then we went and tried this on nickel oxide, and you see if we do this, the as deposited nickel oxide, the work function is about 4.9 before we do that plasma treatment. And what you see here is even though the work function is the same, you again see a substantial increase in VOC. This is not the VOC increase that we saw in going from the SAM modified ITO to PDOT or to nickel oxide at the same work function. There we're talking an increase of 20, 30 millivolts. Here we're talking about a full 100 millivolt increase in the VOC. What's even more interesting is that the JSC goes up substantially and the fill factor comes up quite dramatically as well. So we don't have that kind of kink in the IV characteristics anymore that you have with PDOT. And of course, if we increase the work function of the nickel oxide through this plasma treatment, the device performance comes up. Again, the VOC is 735. The current's exactly the same as S positive. The fill factor comes up. We're seeing about 5% of the system, which previously they had seen less than 2. So the question then becomes, why is that? We don't think, based on what we've done, what I've showed previously, that this is just based on some increase in work function. We have the same work function here, and we have the same work function here, but these device characteristics are very, very different. So what Andres Garcia had done is basically go back and let's just see if we see anything just very simple. Let's do optical absorption, see if you see any changes in the absorption spectrum as you put these on the 2 different contacts. And this is the data he sent, and okay, well, on thick films, the device thickness films of that active layer, you see that there's no real change in the absorption. But if you look closer, and I've gone back and in the paper, this is actually modified, you actually do see a change. What you see is that these have been normalized, of course, and when this nickel oxide system approaches 0, it's very flat. What you see with the P.PSS is there's some slope to it, so it's as if there's a shoulder there. And lo and behold, if you go and make very thin films of this small molecule itself on PDOT and on nickel oxide, you see a nickel oxide absolutely no change in the absorption. You still see the pristine absorption of the film. And when you go to P.PSS, it's redshifted. It just so happens that this is, in the previous slide, swamped by the bulk absorption. So there's some interfacial interaction that's going on to change the absorption locally of that donor material. So in order to test this more fully, we went on and tried a PSS analog just to see if it was the sulfonate that's actually reacting in some way with this donor molecule, so that we can figure out what the mechanism is here in this interfacial chemistry. So what you see is this is a pristine film of the small molecule. We introduce in solution with this molecule this para-toluene sulfonic acid, and lo and behold, you see again this massive redshift in the absorption of that donor material. Aaron went through in some more detail in terms of what this looks like in UPS, and as She is actually actively writing up that study so that we can actually get this, this story kind of closed. But essentially, we go on and do XPS, and Aaron has basically looked at this pure molecule, again on gold, just as the control. What you see is these are the nitrogen 1s spectra here, and the data doesn't show up very nicely, but it's these gray dots in the background. Basically just trust the fits that are there.
They're great at fits.
Yeah.
They can all do fits now.
They can all do fits, and if you work on a PC, you can actually see the data. You paste it into a Mac and it never shows up. But essentially what you see is it looks like there's one peak here, but it turns out it can't be one peak because there's two nitrogen species in the molecule. And so when you break that up, Aaron has fit this in a 2-to-1 ratio of these thiodiazole nitrogens versus the pyridyl nitrogens. So these obviously are in a 2-to-1 ratio atomically in the molecule. That doesn't change ever unless there's something coming in from the atmosphere or something like this. And so basically what you see is two peaks. When we introduce this para-toluene sulfonic acid, you see that you still have those two peaks, but now you have two new peaks, which are related to a protonated nitrogen species in those systems. So what we'd like to do then is to go back to the nickel oxide PDOT-PSS comparison and do the same thing. And when we do that on nickel oxide, this is a thin film, and this is a very thin film. In this thin film on nickel oxide, again, you see absolutely no changes in that in the XPS data. The peaks are the same, no matter what the thickness is. They look exactly like the bulk. When you look at that same film on PDOT-PSS, you see that in the thin film you have two, I would say, relatively weak shoulders, but this is thickness dependent. So this is clearly a reaction at the interface, because as we make that film thinner, the XPS is very surface sensitive, as I'm sure Aaron went through. And so if you have a thin film, you're looking at the top surface and probing some small depth into the film. But if we make the film thinner, then you're looking more closely near the interface. And that's exactly what you see here, is that, as you make that film very thin, you still see the bulk peaks, but then you see that these protonated peaks are dominating the XPS spectrum. We've gone back and we've done a lot of characterization on the system in terms of titrations and NMR, and sure enough, it is a real protonation, which agrees with the XPS data that Aaron started off with. So what we think is going on here then is that there's no protonation of nickel oxide contact, and it works very well, but there is a substantial protonation, basically a hydrogen bonding to these nitrogen atoms in these pyridyl thiodiazole in these small molecules, and that changes the band alignment locally at the interface. It pushes everything deeper so that effectively you have a very effective hole or barrier for hole transport or collection out of the device, which is actually a protonated species of the donut itself. It has nothing to do with the PDOT. The PDOT is essentially unchanged. This has been a collaboration with Guy Bazan and Greg Welch at UCSB, and as a part of the Center for Energy Efficient Materials there, which is an EFRC based at UC Santa Barbara. We've said, okay, well, this is why this system doesn't work at all on PDOT. So they said, okay, well, we're chemists, what else can we do? We can go and actually try to make an equivalent material without the nitrogen, but it turns out that blue shifts the system quite dramatically. The device performance out of that is about 2 or 3%. It's actually quite poor. They're reporting on that now. If you go to this fluorinated benzothiodiazole system, so basically you replace this nitrogen here with a carbon-fluorine bond, you see that now the device performance on PDOT is over 7%. And that's simply by changing that interfacial chemistry. So on molyoxide, if we had the same molecule, which we don't, if we had the same molecule on nickel oxide, we should be getting close to 7% for this system on nickel oxide or moly oxide, but on P dot it's 2. If you simply change the chemistry at that interface, now you solve that problem, eliminate that chemistry, and now the device performance is very, very good. So the last thing I just want to touch on are inverted device architectures. This is basically just inverting the polarity of these devices using higher work function back contacts and those effects on degradation and device lifetime. So a long time ago, Matt White and I were working on hybrid devices, and in order to make them work better, we used a P3HT PCBM blend in some nanorods on zinc oxide, and it turns out if you take out the nanorods, you can just make an inverted P3HT PCBM cell. This was at the time about 2.5%, 2.7%, something like this. Now we're basically getting equivalent performance to our standard devices, and this is because instead of just using silver, we're now using a P dot layer at the interface. But what these zinc oxide layers allow you to do as well is again, as Joe probably pointed out, replace that ITO with other TCOs that might be higher performance and or cheaper. And you get more or less exactly the same performance. The change here in the photocurrent that you see is dependent solely on the transparency of the TCO itself. So the AZO transparency isn't quite as good as the IGO or ITO. We're using a diethyl zinc precursor on all of these TCOs, which is a solution deposited system, and it's processed at 110C. And that's actually important because some of these TCOs are actually temperature unstable at higher temperatures. So if we anneal our typical zinc oxide or nickel oxide systems at 300 degrees, then actually I think it was the IZO that actually failed, and we saw some pretty poor device performance. Anyway, just to touch on stability a little bit, what I want to show you is if we go to these two different device architectures. This is our standard device architecture, P dot on the bottom, aluminum or lithium fluoride aluminum on the top. You see that under constant illumination and load, so we're illuminating these devices with a resistive load, you see that the devices are literally dead within about 10 or 20 hours in air, unencapsulated. And basically, this is arguably where OPV gets its bad reputation for having very poor lifetimes. But what you see here unequivocally is that it's not dependent on the active layer or in fact the organics at all. This change in stability is simply due to very unstable contacts. This lithium fluoride aluminum contact is very, very unstable. And so if we simply invert the architecture, we still have P dot in this device stack on top. We see dramatic changes in device lifetime in these systems, orders of magnitude changes just by doing that simple thing. However, that P dot PSS layer is still not stable. It is still causing some degradation. So what we've done here is look at two different devices, basically one with just silver on the top and one with P dot silver on the top. And we've worked with Craig Peters at Stanford and Mike McGee's group. He's done photocurrent maps. Basically what you see is this is the device as received at Stanford. He does the photocurrent map. You see some defects in the film, sure, but you take and age that and you see massive degradation locally. So you see edge-in degradation in the sense that the device electrode is going laterally across the screen, and you see edge-in decay. So you can actually see here, if your vision is okay, that there is some collection here, and it's basically decaying in from the electrode edge. The other thing you see here is that anywhere you had a defect, initially now you have massive failure of the device entirely. So we don't have decay uniformly across the device area. We have the device that's working very well in most areas until these defect areas grow and the current drops essentially to zero. If we look at silver only, you see something very different. Here you see the device is still decaying, there's no question about that. But what you see is that it's quite uniform, relatively speaking. In addition, there's no edge-in decay either. The device area is the same as it was when it started. So this is indicative of some very different degradation mechanisms with those PDOT PSS layers. We can go and actually change that top contact thickness of the silver. You can see that the catastrophic failure you see in these PDOT PSS-based inverted devices is just extended. They always catastrophically fail. Depending on how thick that top contact is, we can delay it. And we can actually go to, you can't really see this here, I apologize, but this is a silver, 100 nanometer silver layer with a 100 nanometer of aluminum layer on top. And our unencapsulated inverted devices are lasting now beyond 5,000 hours before they hit the 80% of their initial value. And that is, again, simply by changing this degradation or pathway through the contact. You still do see this initial degradation of the first couple hundred hours, and we still think that that's related to edge-in decay that you see, irrespective of the top of the contact. Basically, if you encapsulate those, we can measure these for a year, and they're quite stable. So there's hope for OPV yet, I would say. Much to do, but we're getting there. So with that, I just have some conclusions, but I won't go through these and just ask for questions, comments.
Are there some urgent questions? Yes.
With respect to the appropriation issue, when donor got or acceptor got changed to that CF nitrogen, you still have those other two nitrogens in there that I assume would also get eliminated. Why did that seem to shut off so quickly?
They're much less basic. No, those other two nitrogens are much less basic. We've done a bunch of calculations with Guy Besson's group, and you see that yeah, the activity of those nitrogens is orders of magnitude lower in terms of the protonation reaction. So they're still there. Do they still play a role? Maybe. Not much.
So are there systems where PDOT is a better choice, or from what you're saying, it's often looks like sort of throwing out the window for the same concept?
I'm not familiar with any real system where PDOT is a better choice, no. It can have equivalent performance if you have a system with fairly low ionization potential, like P3HT, for example. Anytime we make P3HT with any nickel oxide, any moly oxide, any of these oxide contacts, they all work basically the same as PDOT. It works very well for PDOT. But as soon as you increase the ionization potential, move these things deeper, then all these things start to play a much, much stronger role. Now, is there hope for that fluorinated small molecule on some metal oxide system? We sure hope so, but thus far we haven't gotten there.
Okay, one last question.
You talked about transmission. Nickel oxide is a better transmission than PDOT. What about reflectance of the device? Can you comment?
Yeah, I mean, there's definitely a change in index, for example, between the PDOT and the nickel oxide. The reflection, I don't think that, I know that we've measured it, but I don't think that it was changed much at all. Basically, it's yeah, I mean, effectively the transmission has increased, and I don't think the reflection changed much.
Okay, let's thank Dana again. We have 5 minutes.